In this video, we're going to talk about how to calculate areas and volumes using polar double integrals. So 3 formulas we want to be familiar with. We could talk about the area of a region R. So we said before that area is going to be the double integral over a region R of dA. And in polar coordinates, dA looks like r dr d theta. We could also talk about the volume under a certain surface. So imagine if we had a surface, say z equal f in space, and then we had a certain region that we're interested in finding the volume over that region. So visually our volume would look something like this. So we want to capture all the points that have xy values sitting over that region R, and that have z values on or below that surface and on or above the xy plane. Okay, so geometrically that's what we're trying to capture. And then let's think about how we would express such a volume in polar coordinates. Just like with rectangular coordinates, you could say volume is the double integral over r of f times dA. But if we're in polar coordinates, then our dA again is going to look like r dr d theta. And then we could generalize this formula a little bit by talking about the volume between two surfaces. So let's say we've got a surface z equal z top, and then another surface, say z equals z bottom. And we want to find the volume between those two surfaces, but over a certain region in the xy plane. Then we would just trace our region up, figure out where it would cut through our surfaces, and then we're just trying to capture the points that lie above that region R, but between those two surfaces. So if you think about the height of each of these little columns that we might draw within our volume here, the height is just going to be the difference z top minus z bottom. So this leads us to a similar formula as we had for rectangular coordinates. The volume would be the double integral over r. What we'd be integrating, z top minus z bottom. And then we would need to multiply that by dA, which in polar coordinates is going to look like r dr d theta. So same three formulas as we had for rectangular coordinates, just with dA written as r dr d theta. So over the next few videos, we're going to do 3 examples. We'll practice each of these formulas and get comfortable with polar coordinates. What we'd like to do in this example is to find the area inside the curve r equal 3 plus sine theta and outside the curve r equal 2 using a double integral. So first thing we should do is draw a picture and try to graph these two polar curves. So I'm just going to go 4 units out along our x and y axes here. And let's start by graphing the curve r equal 2. So r equal 2 just means capture all the points that are at radius 2 or distance 2 from the origin. So remember, radius just capturing the distance from the origin. So if you have r equal constant, that is giving you a circle centered at the origin of that radius. So next we want to graph this curve here, this r equal 3 plus sine theta. So a quick way to do that, let's just think about a variety of different angles and figure out what radius is going to go with them. So if our angle theta is 0, sine theta is 0, and that makes our radius value equal to 3. So angle theta equals 0 is going over here, and we're saying at that angle, radius is equal to 3. So that gives us that point. When theta equals pi over 2, well, sine of pi over 2 is 1. So at that point, the radius is going to be 4. Okay, so at an angle of pi over 2, that's up here, we're getting radius 4. So that gives us that point. And then similarly, at an angle theta equal pi, well, sine of pi is 0. So we're back to radius equal 3. That gives us this point here. And then by the time we get around to theta equal 3 pi over 2, Well, sine of 3 pi over 2 is -1, so our radius is going to be 2 at that point. So angle 3 pi over 2 corresponds to radius equal 2. All right, so we've got 4 points here. If we just draw a smooth curve joining those 4 points, we get something that looks like that. All right, so what we want to do is find the area inside the blue curve and outside the red curve using a double integral. So what we're going to imagine doing, we're going to try to describe this region R by drawing a whole bunch of little rays that are going outwards from the origin. So you'd have, let's start drawing these in black. So you'd have these little lines that are just radiating outwards from the origin. And if you drew infinitely many of them, they would cover this whole entire region R. So let's try to come up with a description of our region R. We need to talk about what radius values will we be running through and what theta values will we be running through. So each of these little rays here is going to run from R equal the inner circle to R equal the outer curve here. The inner circle has equation R equal 2. So R is ranging from 2 out to this outer curve here, which has equation R equal 3 plus sine theta. So might have been helpful here to label those two curves. Okay, so R ranging from 2 to 3 plus sine theta. And then as we cast a glance over our picture, what angles are we seeing in our region R? Well, all of them, everything from 0 to 2 pi. So that's a description of our region R. Okay, and from there we can say, well, area is going to be the double integral over our region R of dA. But if we want to make that dA explicit, we should write r d theta, because that's what dA is equal to in polar coordinates. And so with that, we can plug in the appropriate limits of integration onto our integrals and then go from there. So R values ranging from 2 to 3 plus sine theta, and theta values ranging from 0 to 2 pi. So if the problem had just asked us to set up the double integral, then we could have stopped there, but we are being asked to find the area, so we're going to actually do the computation here. Let's keep the outside integral on there. We'll keep the d theta on there, and we'll just work on the inside integral here. Integrating r with respect to r is going to give us half r squared. So I'm going to put the half out in front of the integral, and then we need to evaluate this r squared at r equal 3 plus sine theta, and then r equal 2. Okay, so we've got half the integral from 0 to 2 pi, d theta at the back, and let's do our evaluation here. So we're going to have 3 plus sine theta all squared minus the square of 2, which is going to be 4. Okay, and we'll actually simplify this in our next step before we go on to integrate with respect to theta. So we've got 1/2 integral from 0 to 2 pi. If we expand the square, we get 9 plus 6 sine theta plus sine squared theta. And then that's minus 4. So I might just turn that 9 into a 5 to make things efficient. And then this is going to get integrated with respect to theta. So a couple of handy identities that tend to come up when we're doing polar double integrals. Sine squared theta is the same thing as 1 minus cos 2 theta over 2. And cos squared theta is the same thing as 1 plus cos 2 theta over 2. So these identities are helpful because it's difficult to integrate sine squared theta directly. But if you use this double angle formula, then pretty easy to get the integration done. So when we see this sine squared theta here, we actually want to reimagine that using our top identity here. So let's call this 1/2 minus cos 2 theta over 2. And you could even take that a little bit further, cross out the half, and maybe add it to the 5, so that you could say overall you've got 11 halves. And that way we're set up for our integration in the next step. So we're going to be integrating 11 halves plus 6 sine theta minus cos 2 theta over 2. So we'll keep our half out in front here, and we can now do our integration. So integrating with respect to theta, we get 11 halves theta minus 6 cos theta, and then minus sine 2 theta over 4. And that needs to get evaluated at theta equal 2 pi, and then theta equals 0. Okay, so we're getting close to our answer here. Let's do our evaluation at this point. So plugging in theta equal 2 pi, we're going to get 11 pi for our first term. Cos of 2 pi is 1, so we're going to get minus 6 for the second term. And then sine of 4 pi is 0, so that last term is a 0 there. And then we need to subtract off what this is equal to at 0. So we get 0, we get a minus 6 coming from the middle term there, and then we get another 0 coming from the sine term. All right, so that minus 6 and the plus 6 here are just going to cancel, and final answer coming up, 11 pi over 2. So that is the area inside our region. Let's go back and look at our picture. So the area inside the blue curve and outside the red circle, 11 pi over 2, and we accomplished that using a double integral in polar coordinates. Thanks for watching.